This video will introduce you to the basics of capacitors, which are devices used in circuits that are extremely important to all of our electronics that we use in our daily lives. This is chapter 25 in your textbook, and as you're looking through the textbook, we will not cover the information in section 6 of chapter 25. You're welcome to look at the learning objectives for this chapter on the notes slides, but we're going to jump right in and learn about what a capacitor is. Before we can learn what a capacitor is and then also about capacitance. A capacitor is actually a relatively simple device. It's just two isolated conductors. They can be of any shape, and they must be separated by some distance. Saying that these conductors are isolated simply means that they are not touching another conductor, other than perhaps the wires that may connect them to other parts of a circuit. Capacitance, on the other hand, is a measure of how much charge must be put on the plates of a capacitor to produce a certain potential difference between them. When I say on the plates of the capacitor, that's really just a quick way of saying on the conductors, on those two conductors that make up a capacitor. Often those conductors are plates, so two-dimensional objects, but we'll actually see some examples of things that are not plates, but rather are cylinders or spheres or some other regular shape. That term capacitance is going to be really important to us as we study capacitors. And we're going to summarize that definition using a equation. So saying that capacitance, or the letter C, it says it's how much charge must be put on the plates to produce a certain potential difference. The way that that shows up in an equation is that capacitance is equal to the magnitude of charge on a plate divided by the potential difference between the two plates. When using this equation, we know that charge must be in coulombs and potential difference is in volts. So that means the units for capacitance would be coulombs per volt, and we have another name for a coulomb per volt. We call it a farad, and we abbreviate that with a capital F. So farads are the unit for capacitance. 1 farad is a very large unit. Think about it. That would be 1 coulomb of charge per 1 volt. And we know 1 coulomb of charge is a lot of charge. Typically, capacitors are in microfarads, nanofarads, or sometimes even picofarads. But most of the time, we're dealing with pretty small capacitances. Next, we're going to talk about how a capacitor gets charged, or how it stores electric potential energy, which is its main purpose in a circuit. The first we're going to start off is a fact. When a capacitor is charged, its plates have charges of equal magnitudes but opposite signs. To understand why that's the case, we have to understand the process of charging a capacitor. Let's look at a diagram here. One thing I want to point out in this diagram is that I've modeled my capacitor as being two parallel plates or two parallel two-dimensional surfaces. However, as I've already mentioned, that we can have any shapes of conductors. And even if we did have a cylindrical capacitor, for example, which would be one cylinder inside of another, or perhaps a spherical one, we would still model them as the parallel plates like you see here. The other thing that appears in this diagram is the symbol for a battery. That's this symbol at the bottom here, one long line and one short line. And just a reminder, that long line is the positive side of my battery, and the short line is always the negative side of my battery. Often when we're looking at circuits where we have a capacitor in them, there'll be some sort of switch, meaning that the circuit will start out as an open circuit. And so that would mean that kind of this region here would not be connected. And so nothing happens with the capacitor. It's just uncharged conductors. However, as soon as we would close that switch, charges would flow. And we know that in conductors, it's the negative charges that flow through conductors. So that means that if I have a single negative charge, that negative charge is going to come from the negative side of the battery, and it's going to move around my circuit. So it goes up through these wires, and then it comes to this conducting plate right here. And because there's no conductor in between these two plates, this electron cannot jump this surface to get back to the other side of the battery. So it just kind of gets stuck on this plate. But as a result of it being stuck on that plate, one of the negative charges from the positive, from this other plate, would get repelled off and would travel down my circuit and then through the battery. When it goes through the battery, it picks up some energy, and then it would go through this circuit and once again be stuck over here. And again, because there's now two extra electrons on the plate on my right-hand side, we would have another electron leaving this other plate and repeating this process. And notice that every time we have an electron leaving, we're leaving behind a positive charge that is an unpaired positive charge. In other words, we started out with these pairs of positive and negative charges. And we've actually removed a couple of those charges from over here. So let's go ahead and remove a couple of those negative charges. And of course, we still have positive charges over here, as well as some negative charges that were initially there. These plates started out neutral. But now my right-hand plate has excess negative charges, and my left-hand plate has excess positive charges. So that means that we all of a sudden have a positive plate and a negative plate. And because those charges all came from one plate and went to the other, the two plates have the same magnitude of charge. They're just different signs. Now let's say we get these plates fully charged. So when these get to be fully charged, that'll end up meaning that we get to a point where the battery does not have enough energy to be able to move any more of the negative charges from the left-hand plate around to this right-hand plate. Now, I'm not drawing all the charges on these conductors. I'm only drawing the excess or the unpaired ones. Let's say then that we all of a sudden get rid of this battery from my circuit. Instead, we just have a conducting path from one plate to another. If that's the case, then all of these negative charges are going to travel around that conducting path and go back to their paired positive charges, which then means that all of a sudden my capacitor is neutral once again. Now, this process doesn't happen immediately. It does take some time for a capacitor to charge and for a capacitor to discharge. Hopefully that makes some sense, because if you think about it, as this right-hand plate would become more and more negative, it would be harder and harder to push that electron around the circuit to that plate. So it takes a bit more time for that to happen. Eventually, though, we do reach kind of an equilibrium state where the capacitor is fully charged, and it'll remain fully charged until you provide a path for discharge. We'll have some experiences with circuits containing capacitors and looking at their charging and discharging, how much time it takes for them to do that, and really the process that they go through as they charge and discharge. Stay tuned for learning more about calculating the capacitance of an individual capacitor.